And do this practice exam number 2. This is, I don't even know what chapters. Something like 3 through 5, but definitely 4 and 5. So, yeah, let's go ahead and get through it. There is some earlier stuff in here, but again, you need to know nomenclature. If you don't know nomenclature, go back to pages, look at exam 1 material, and learn nomenclature. I've taught it a few times, and so I'm not going to teach it in this particular one, but it's worth going back if you're feeling unconfident in it. All right, so let's go ahead and get started. I essentially just ask you to name these. I give you some hints. I say pay attention if they're a metal and a non-metal, and if they are a metal and a non-metal, do you know their charge of that metal? If you know the charge, you won't be using your Roman numeral, and if you don't know the charge, you will be using your Roman numeral. All right, so calcium. Everything we know a charge of is in the first or second column, because these things in the first column will be a 1+ charge, things in the 2 column will be a 2+ charge, the second column. And then we know that one little triangle, if you remember, it kind of goes like this, where these 3 things are 3+, these 2 things are 2+, and silver right here is 1+. All right, so the first thing we come across is calcium chloride. We know the charge, I gave it away already. We know the charge of calcium. It's in the 2+ column. That's why this is calcium chloride. I strongly suggest going back and forth. So once you figure out the name, go back and try to get that formula and ask yourself how we built that formula. Why didn't we need anything other than just the name calcium chloride? The next one is aluminum. Aluminum happened to fall in this little triangle right here. It's got a 3+ charge. So we know its charge, and therefore this is just aluminum oxide. Now we get to copper. Copper is not in that triangle that we have. Copper is over here in the transitional metal area. And because of that, we don't know its charge. Therefore, we have to figure it out. We can figure it out because we know oxygen has a 2- charge, and we know that there's only 1 copper. So we can figure out the charge that copper must be in order to cancel out that 2-. It must be 2+. And that's why this is copper 2 oxide. Pay attention to the endings. This is "-ide", "-ide", "-ide". Why are they "-ide"? Because it's a metal paired with a single type of non-metal from the periodic table. But now we come across something different. It's these polyatomic ions, the SO4. How we work with polyatomic ions is we have to just memorize them. I showed you how to do it. There's another video showing specifically how to memorize polyatomic ions, but you need to know that this particular polyatomic ion is sulfate. We also know that lead here is not part of the first or second column, and it's not part of the triangle. Therefore, we don't know its charge. Therefore, we have to use Roman numerals. So sulfate is SO4 2-, and there's 2 of them. In other words, we have a total charge of 4- coming from over here. If we have 4- coming from over here, what must the lead be? It has to be 4+. And that's why this is lead 4 sulfate. I can see people getting frustrated. I'll put that negative sign over there for you. All right, now we're on to this. Whoa, get it? Okay, so WO2O2. We know each oxygen is 2-. And we know that W, we have no idea what its charge is. So we're going to have to use Roman numerals again. But if this has a total of 4- from over here, you know that this must be 4+. And that's why this is tungsten 4 oxide. Again, pay attention to the endings. This one ended in "-ide" because it's just one thing from the periodic table. This ended in "-ate" because this is sulfate. All right, now on to the next one, NO2. NO2, we're talking about stuff up here, nonmetals. So when you have 2 or more nonmetals paired together and there's no metal there, that's when we're going to be using the other type of naming. That's when you can use the di-tri. There's 1 oxygen, or excuse me, 1 nitrogen and 2 oxygen. And this is why this is nitrogen monoxide. If there had been 2 nitrogens, we would have said dinitrogen, but because there's only 1, we don't start with mono. And again, that's something you can go back and watch the video about naming to remember. Here we have 2 nonmetals again, phosphorus and oxygen. There are 4 phosphoruses, phosphori. This would be tetra. Phosphorus. Deca is how you would write, if this were an A, deca is how you write 10, but because it's oxide, you kind of combine it and write decoxide. I wouldn't have decaoxide as one of the options. That's not what I'm testing, whether or not you can pair vowels together. I just want to know, do you understand the tetra? Do you understand this? And also pay attention again to the ending. All of these non-metal compounds, molecular compounds as they're called, will end in "ide." Holy moly. All right, for this I realized I didn't grab my calculators. Give me a sec. I'm gonna grab it. I grabbed it. Okay. So, just as a reminder, we use dimensional analysis to kind of go from grams to mole to molecule to atom and back. All right, so what I want you to do in each of these, we're going to start with the grams, turn it into mole, start with the grams, turn it into molecule, start with the grams, turn it into atoms. That way we cover all of those portions of questions I might ask. Step number 1, write down what you got. We got 48.6 grams of this copper 2 nitrate. Copper 2 nitrate is CuNO3 2. That's because copper has a 2+ charge, nitrate is a -1, and we needed 2 nitrates to cancel out that copper. If you don't know what that is, you're going to be in trouble because this is how I would ask the question. All right, so how many mole is it? I gave you the molar mass. I will likely give you the molar mass unless I'm specifically asking you about it. And if I don't give you the molar mass, feel free to ask me in class. I probably just made a mistake. All right, so we got 48.6 grams. If this is grams, we know grams go here. It's 187.56 grams per mole. So I take 48.6 divided by 187.56. And I get 0.259 mole. I used 3 sig figs because this had 3 sig figs. And this had 5. All right, so that's how many mole we had. Let's move on to the next question. You don't want to round. I don't want to take this number and then apply it here. For the next one, I'm just going to do the whole thing. So it says how many molecules. When they're ionic compounds, they're technically called formula units. I generally just call them molecules, and I try to let you know that from the start because molecules just, it's easier. It rolls off the tongue a little better. And it's not as scary sounding, in my opinion. All right, so we got 48.6 grams, but this time we got to go from grams to mole and then from mole to molecule. So let's do it. So 48.6 grams, we know there's 187.56 grams in a mole. That brought us to mole count. Now we got to go to mole to molecule. The conversion that has moles and molecules in it is that a mole has 6.022 times 10 to the 23rd molecules. In fact, that's what a mole is, 6.022 times 10 to the 23rd of anything. And I get an answer of 1.56 times 10 to the 23rd. Because I'm doing this live, I'm going to go ahead and do that again. And I get the same answer. Great. Okay, now it asks us, that was molecules. Now it asks us to go all the way to atoms. Well, we know that a single molecule of this nitrate has 6 oxygen atoms. It specifically says oxygen atoms. Pay attention to that. That's something that might be easily missed in an exam. And if you don't know that it has 6, let's break it down just to make sure you're comfortable with that. It's copper and 2 nitrates. Each nitrate is a nitrogen with 3 oxygens on it. So when we're saying copper nitrate, this would have a 2+ charge, and each of these would have a -1 charge. Or copper, a nitrogen, 3 oxygens, a nitrogen, and 3 oxygens. So our total oxygen in the sample is 6 oxygen atoms per molecule. And I hope you agree. Okay, so now that we have this conversion, we can just kind of add it on the end of this. That gives us all the information we need. So we got 48.6 grams. We know there's 187.56 grams per mole. That took us from grams to mole. Now we go from mole to molecule. Remember to go from mole to molecule. You know the mole has 6.022 times 10 to the 23rd molecule. And now we're in molecule town. Now we can go to atom town. To do that, we know a molecule of this CuNO3, 2, has 6 oxygen atoms. So 48.6 times 6.022 times 10 to the 23rd times 6 divided by 187.56 gives me an answer of 9.36 times 10 to the 23rd oxygen atoms. All right, so hopefully that's what you got. I'm gonna move on. So a sample of P4O10 contains this many phosphorus atoms. Now it's giving us atoms, and it asks you for the mass of the sample. So essentially it wants us to go from atoms to grams. So we just have to reverse the process we just did. Let's go ahead and start with atoms. 4.37 times 10 to the 25 phosphorus atoms. And it's P4O10. So we know that one molecule has 4 atoms. In other words, if this is phosphorus atoms, we have to put phosphorus atoms down here. We know we gotta turn it into a molecule. The question is how many phosphorus atoms in a molecule, and that answer is 4, because that's why it's P4O10. Now we made it to molecule town. Now we can go to mole and then grams. We know the conversion between molecule and mole is that there is 6.022 times 10 to the 23rd molecule per mole. And we know the conversion between mole and grams is the molar mass, which is in grams per mole. If this is mole, we have to put mole here, and our 283.99 grams goes on top. Okay, I'm going to break this down a little more because I think a lot of people, it scared a lot of people when you got 10 to the 40 something, because that's not what you're supposed to get. The reason you got 10 to the 40 something is because you didn't use a division sign here, and essentially that tells the calculator to put that 10 to the 23rd up here. And then you're taking 10 to the 25 times 10 to the 23rd, screws it up. So here's how we're gonna do it. I'm gonna take 4.37 times 10 to the 25 times 283.99. So everything on top I multiply, and then everything on the bottom gets a division sign, divided by 4, divided by 6.022, divided by 10 to the 23rd. If you have another way that works, that's fine, as long as it works. There are several different ways to skin this cat. So 4.37 times 283.99 divided by 4. And I get 5,152, I believe, which would be, with 3 sig figs, 5.15 times 10 to the 3rd grams, or 5,150 grams. I'd accept either answer. I'm going to go through and do it again in case I messed up. I suggest you do the same on an exam. And I get the same answer. All right. Moving on. Okay. So now we're at molecular shape and Lewis structures. I'm going to go ahead and use a piece of paper to draw each Lewis structure as we go. So the first one is selenium dioxide. Selenium is in the fourth column, so it has 4 valence. And oxygen is the 6th column, it has 6 valence. So for SeO2, we have 4 plus 2 times 6 because it's SeO2. There's 2 oxygens. And that's 16 total electrons. The step number 1 that we talked about is to put the least electronegative thing in the center. If you remember, electronegativity goes up and to the right of the periodic table. So something down and to the left will be less electronegative. Selenium is less electronegative. It goes in the center. Connect your stuff. Add octets to everything. So everything needs 8 things. Remember, a line counts for 2. So this oxygen has 2, 3, 4, 5, 6, 7, 8. Selenium has 2, 3, 4, 5, 6, 7, 8. And this other oxygen also has 8. But if we counted up all the total electrons, we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 20. Do you remember that for every extra 2 valence electrons we have, we need to cross out 2 lone pairs and draw a double bond? And now if I count it again, I still have only 18. So I have to do it one more time. Cross out 2 of those and draw a double bond. So to clear this up a little bit, my structure looks like this. And that's what would go right here. Now we ask for its electron shape. It has 2 electron groups in total. And if it has 2 electron groups in total, that makes it linear. Remember, its molecular shape, as long as it doesn't have lone pairs, is going to be the same. When we're looking at molecular shape, we're essentially looking at the atoms that are attached to the electron groups. So its molecular shape is also linear. Its bond angle is 180 degrees. Hope you agree. A line is 180 degrees. Its hybridization, remember we said S, P, 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 D, 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 D. It has 2 electron groups, so we only underline 2. Its hybridization is SP. And the last question, or the next question is it polar? In other words, if these things were having a game of tug of war, would the selenium move? So this one pulls in this direction, this one pulls in that direction, and the answer is no. You'd equal and opposite force, and it would not move. Finally, we get to bond order. I'm looking for the bond order of just a single one of these. So Se to oxygen. Se to oxygen has double bond. Its bond order is 2. All right, let's move on to the next one. Sulfate. Oh, sulfite. My bad. This is sulfite. And I could have just written sulfite, and you should know what it is. Sulfite is SO3, 2 negative. If we look at the valence electrons, sulfur has 6, oxygens have 6, so let's add it up. Don't forget this 2 right here. Let's start with it. Our total valence electrons is 2 plus 6 from the sulfur plus 3 times 6 for each of the oxygens. That's a total of 24, 25, 26. All right, let's do our plan. We're going to draw sulfur. It's going to have 3 oxygens on it. Let's give everyone an octet. we go. So now 2, 4, 6, 7, 8. That sulfur has 8 around it. Each oxygen has 8 around it. And now let's count. See where we got. What we got. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. We got 26. Woohoo! Good job. So as far as I can tell, it's good to go. You will eventually learn that there are other options. You might have drawn it this way. And if you draw that structure, you would also have it correct. The bond order in this one is also correct. Bond order. And this one is 1. The bond order in this one, each one has at least 1, and then it's sharing this other one. It resonates. It's 1/3. So I would accept either answer. This one's the way I taught you, and that's probably the way that I would expect you to do it. So if we go and do this, there we go. Now this shape right here, the electron shape, there's 4 electron groups. They're trying to get away from each other as much as possible. That gives you a tetrahedral. Tetra. It's as much as I'm going to fit there. But its molecular shape, we're only looking at the 3 groups, 1, 2, 3. And those form a trigonal pyramidal. Now tetrahedral has a 109.5 bond angle, but because you have this extra lone pair, you're pushing those things down, whoosh, getting even closer, and so that's why it's less than 109.5. It has 4 things around it. So for our S, P, 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 D, 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 it goes, we underline 4, and it's sp3 hybridized. Then it asks, is it polar? Well, these things aren't in a plane, right? They look like a triangle, like this. And so if you have one person pulling this way, one person pulling that way, and one person pulling that way, that sulfur is going to move. And therefore, it is polar. And again, its bond order would be 1. All right, let's look at beryllium chloride. Beryllium chloride is BeCl2. You should recognize right away that boron and beryllium don't need octets. Those are the 2 exceptions. Boron and beryllium don't need octets. All right, beryllium has 2 valence electrons, and each chlorine has 7. So we have a total of 2 plus 2 times 7 for a total of 16 valence electrons with this beryllium dichloride. We just go ahead and draw it the way we know. We got a beryllium, chloride, chloride. We give everything an octet. Then as we go to do beryllium, hopefully we remember that it doesn't need an octet, but even if we forget, let's do it the way we might do it in class. And then let's count electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We got 20. You know chlorine only likes to make a single bond. So this should be your stop. Normally we would cross out 2 and draw a double bond, but you have not seen a double bond to chlorine before. So that should be a big hint that this is that one case where those don't matter. And again, beryllium and boron don't need to have octets. So if we don't care about that, this thing is as happy as can be. It's got 16 valence electrons and it is good. So let's draw it out. We've got a beryllium, chlorine, chlorine. This is linear. It has no lone pair, so it's also linear. Its bond angle is 180. It's sp hybridized. It has equal pole in opposite direction, is not polar, and it has a bond order of just 1, single bond. Last but not least, we get to nitrate. Nitrate is NO3 negative. So if we add up the electrons, we have 1 from this, plus 5 from each nitrogen, plus 3 times 6. Was that 18, 19, 24? So a total of 24 electrons when we put nitrogen in the center, and we add oxygen to it. Give everything an octet, and count electrons. We know nitrogen has to have an octet. It's not beryllium, it's not boron. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. 26, so what do? We cross out 2 lone pairs, and we draw a double bond. If I were to clean this up a little bit, it looks like this. Is that fair? Definitely not fair, because this one has double bond and these two don't. So it resonates, meaning that double bond doesn't actually exist. This one right here, this bond right here, is delocalized and equally shared between all of these. So when we go to calculate bond order, that's where it'll actually make a difference. Because it's delocalized, we know each one has at least 1 bond, and then they're sharing, all 3 oxygens are sharing that 1, and that's why the bond order is 1 1/3. All right, so let's go draw it. If you drew it as the one with the dashed lines, I'd be fine with that as well. Let's look at its shape. It's got 3 things as far away from each other as possible. That's called trigonal planar. It has no lone pairs on it, so it's also going to be trigonal planar. Its bond angle has to be 120 degrees. That's 360. A full circle divided into thirds is 120 degrees each. Its hybridization, it's got 1, 2, 3 things. So for our SPP, it's got 1, 2, 3, and that's why it's sp2 hybridized. Is it polar? Well, remember, this bond is shared equally. So all these oxygens are equal. It's in a plane, so there's 3 things pulling all equally, and it will create a non-polar thing. And again, its bond order is 1 1/3. All right, moving along, y'all. So now it says write and balance the following reaction. It says C4H10 reacts with oxygen gas to yield carbon dioxide and water. You might say, hey, do we really need to know this? Like how to write this reaction? The answer is yes, you do. And you should know oxygen's diatomic, you should know what carbon dioxide is, you should know what water is, and I gave you C4H10. Okay, so once we have this, let's go ahead and balance it. We recognize that this is a hydrocarbon, carbon and hydrogen. That's when we like to CHO it up, but even if you do the H first, that's fine. We should do the oxygen last because it is alone or paired with itself. Don't fill these out first. Stop and do them one at a time, because they're always going to be changing. So only focus on the very first one. That's carbon. On my left, I got 4. On my right, I got 1. 4 divided by 1 is 4, so I put a 4 in front of the CO2. Then I move on to the hydrogen. On my left, I have 10. On my right, I have 2. 10 divided by 2 is 5, so I put a 5 in front of the water. Now we move on to the next one. On my left-hand side, I got 2. On my right-hand side, I got 4 CO2s, which means 8, and 5 oxygens from the water. That's a total of 13. Now, just because that looks funky doesn't mean anything changes. And this is one thing I think in my Monday, Wednesday class, y'all, we didn't quite get here, but I think you can be there now. You just need a little time. So we can go over this in class on Monday again. but 13 divided by 2 is 6.5. And just because it's a 0.5, it shouldn't freak you out. But because you don't like to look at it, and most chemists don't, what we're going to do is get rid of that 0.5. How do you get rid of a 0.5? Well, you multiply it by 2. 50 cents times 2 gives you a whole number, $1. But you don't just do one of these, because that would change the number of oxygen. If you multiply every single one of these things by 2, the ratio won't change, and it'll keep everything consistent. In other words, our final answer is going to be 2 C4H10 plus 13 O2, yielding 8 CO2 and 10 waters. Okay, last but not least, it's kind of one I told you I would give you. It says iron 3 nitrate reacts with sodium chloride in a double displacement reaction. Well, if iron 3 nitrate reacts with sodium chloride in double displacement, that means the nitrate and the chloride are going to switch places. It's going to make iron 3 chloride and sodium nitrate. And you should be able to do this reaction. I would pause it and test yourself if you've got the nomenclature down, because if you don't, nomenclature is almost more important than learning how to balance this reaction. Okay, so I don't know what I'm doing. Iron 3 nitrate would be Fe NO3 3 plus NaCl, and it's yielding iron 3 chloride and sodium nitrate. So when we go to balance this, kind of going from left to right, iron I have 1, iron I got 1, nitrate I have 3, over here I only have 1. So I could start with nitrate maybe. Let's keep going. Over here I have 1 sodium, not gonna do that. Over here I got 1 chloride and 1 chloride. I can start with chloride, or I can start with nitrate. Let's get nitrate out of the way. On my left-hand side, I have 3. On my right-hand side, I have 1 right here. 3 divided by 1 is 3, so I put the 3 right there. There's two options you have. You change the number of sodium so you can move on to sodium next, or we could stick with our plan, which was to do chloride. It's whichever you prefer. But on our left, we have 1. On our right, we have 3. 3 divided by 1 is 3, so I put the 3 there. If you look at iron, we now have 1, and sodium, we now have 3. This thing is balanced. I'm going to rewrite this reaction down here because I use the same one. It's a mini step reaction. All right, so we know we have a balanced reaction now. It says when 5.6 mole of iron 3 nitrate reacts with 4.6 mole of sodium chloride, how many grams of iron 3 chloride? In other words, our question is here, we're gonna find it in moles and then turn it into grams. If you remember, when you're given two numbers, the very first thing to do is find which one you're gonna run out of first. To do that, you divide by the limiting reactant, that by 1, that by 3, and you ask which one's smaller. 4.6 divided by 3 is smaller, and then you get rid of that number. I don't know why I'm whispering. That's gonna be your limiting reactant. Once you find the limiting reactant, you're gonna start with the limiting reactant amount. If this is mole NaCl, you have to put mole NaCl down here, and you have to use the coefficient in front of the NaCl. For every 3 mole NaCl, that's where you put your question mark, 1 mole of this iron 3 chloride. Now we could stop there and then, excuse me, and then later go on and do grams. But remember, it asks grams. So we might as well just keep going. If this is mole FaCl, mole FeCl goes down here. And for every mole of FeCl3, we have a mass of 162.20 grams. In other words, I've got 4.6 times 1 times 162.20, all divided by 3. Let's do it. 4.6 times 162.2. And I get an answer of 248.7 grams. Let me recalculate it and then we'll talk about sig figs. I get the same answer. Great. This had 2 sig figs. Each of these is infinite, and this had 5. So the smallest number is going to be 2. Our answer is 250 grams, or you could have said 2.5 times 10 to the 2 grams. Both are acceptable. All right, y'all, I hope that gave you something to study and look over. And if you had trouble with that exam, well, at least you know where you might need some work or to put your effort in. And have a great weekend, and I will see you all on Monday or Tuesday.